Hey everybody! Today we'll be looking at pressure safety valves, otherwise referred to as pressure relief valves, and the important factors to consider when using them as safeguards in a HAZOP. A pressure safety valve, or PSV, is a mechanically controlled valve that will open when the inlet line to the PSV reaches a specific set pressure. A PSV is used to protect pressure equipment from being damaged in an overpressure event. This diagram shows the cross-section of a typical pressure safety valve. When the pressure under the valve exceeds the force from the spring, the valve opens to allow fluid through the valve. Many factors can affect the reliability and performance of a PSV. Let's join the HAZOP team to discuss the important factors to consider before taking credit for a PSV as a safeguard when conducting a HAZOP.
So we have PSV-1 and PSV-2 as potential blocked flow overpressure protection safeguards on the free water knockout. But first, we need to see if the PSVs will be effective and how much credit we can take. What is the set point of the PSVs?
Both PSVs have a set point of 9,930 kPa(g), which is low enough to protect the vessel V100, which is rated for 9,930 kPa(g). I always look at the pressure rating of the equipment that the PSV is supposed to protect, and ensure that the set point is low enough to prevent overpressuring the equipment.
Okay, that's great. The PSVs are set to protect V100. But what about the sizing case?
The sizing case shown on the P&ID is for the governing case. These PSVs are sized for the governing case of blocked flow overpressure. It can still be sized to protect against thermal, fire, reverse flow, valve failure, etc., but not be listed on the P&ID.
That's good that we checked that the PSVs are sized for blocked flow overpressure. Let's take credit for them now.
Well, there are still a few more things we need to check, like the relief location. Does the PSV relief go to a safe location?
Yes, the relief of these PSVs go to flare.
Why don't we just vent to atmosphere? That would be more cost-effective.
Well, if we vent to atmosphere, there could be a risk of fire or explosion if the gas was exposed to an ignition source. We would also risk personnel exposure to sour gas. I wouldn't put my operators at risk by venting to atmosphere.
Exactly. That's why we designed the relief of the PSVs to go to flare. I have checked the flare capacity and can confirm that it is able to handle the maximum potential volume from the PSVs. The other thing to check is the open flow path. For a PSV to be effective, there must be an open flow path to the relief location. To achieve this, there should be an open flow path from the equipment to the PSV inlet and from the PSV discharge to the relief location. I always make sure that any manual valve on these flow paths are locked open with administrative controls so that there is no potential blockage.
And there shouldn't be any other potential blockage on the relief path. I've dealt with freezing and plugging of equipment on the relief lines. If freezing is possible, it should be checked that there's heat tracing on the PSV and the piping with an alarm or indicator to detect heat tracing failure.
Too bad we're not in Hawaii. Then we wouldn't have to worry about freezing.
Well, we do have a check valve on the common outlet of the PSVs. This could potentially freeze. Also, depending on the design of the PSV, back pressure on a PSV could prevent it from lifting at the required set point. If a PSV is set at 9,930 kPa(g), but has 70 kPa(g) of back pressure on the discharge side, it may not lift until the suction side reaches 10,000 kPa(g). This could prevent the valve from effectively protecting against overpressure. Even if the valve does lift at its proper set point of 9,930 kPa(g), it might not be able to relieve enough flow through the valve with 70 kPa(g) of back pressure. Back pressure on relief devices should not prevent the PSV from protecting against an overpressure event.
The American Petroleum Institute standard, API 520, does not allow for check valves on relief lines. We should make a recommendation to ensure that the check valve is removed before we can take credit for the PSVs.
Okay, then after the recommendation, how much credit can we take for these PSVs?
It depends on the type of service. For clean service, such as pure gas, the PSV reliability can be taken as 99%, while for dirty service, no credit can be taken due to potential plugging. This is in line with guidelines from the Center for Chemical Process Safety.
This is a very clean service, so the PSVs should be very reliable, 99% for each. We haven't seen any wax or any sort of plugging during plant turnaround inspections.
Given that both are sized to independently relieve the required volume, we can take 99% reliability for the first PSV. However, for the other PSV, the reliability should only be taken as 90% due to the potential for common cause failure, as they are exposed to the same process conditions and therefore could be exposed to the same fouling and plugging. This also corresponds to the Center for Chemical Process Safety guidelines.
One last thing we need to check is the JT effect across the PSV. We have had some issues in the past with the temperature going below minimum design metal temperature.
What's the JT effect?
The Joule-Thomson effect occurs across the valve when the fluid expands from high to low pressure, which can result in a significant temperature drop. The discharge piping then has potential to go below the minimum design temperature, possibly leading to piping integrity issues. We haven't checked the JT effect across these PSVs, as I didn't think that it would be an issue. But since you've had previous JT problems at this site, I will run some calculations.
So we can't take credit for the PSVs at all?
No, we'll have to make a recommendation to check the JT effect across the PSVs and ensure that it is not an issue before taking credit. If the JT effect is an issue, we may have to redesign the flare system, increase the pressure rating of the piping, or install a high-integrity pressure protection system.
We don't have the time or money to do that.
Compromising the integrity of piping is not something I'm comfortable with. We should make sure that the discharge piping on these PSVs are designed right to ensure the safety of my operators.
Pressure safety valves are important safeguards for overpressure protection and are often used in HAZOPs. To summarize, the main details to check when taking credit for PSVs in a process hazard analysis include set point, sizing case, relief to a safe location, open flow path, back pressure, type of service, common cause failure, and any unique issues for a given process. These considerations are important in ensuring PSVs can reduce overpressure risk reliably.